Welcome back to part 2 of our journey into implementing an industrial temperature control system using TwinCAT's TF4110 temperature controller. In part 1, we laid the groundwork by exploring the theory and structure of the TF4110 function block in depth. If you missed it, I highly recommend checking out part 1 before diving into this installment. Today we are stepping away from the theoretical and getting hands-on in TwinCAT. I'll be guiding you through the process of writing the code to bring this powerful function block to life. We will be using TwinCAT's TF4110 function block and implementing a multi-zone temperature control system and make use of solid-state relays to control the switching of the various heaters. The power delivered to the heaters will be pulse width modulated at high speed, and temperature control can be achieved by varying the duty cycle of the pulses. Finally, to achieve full closed-loop controls, we will make use of the thermocouple feedback to measure the actual temperature of the process and tie them back to the control system. By the end of this tutorial, you'll have a solid understanding of how to implement the TF4110 in practice and see its application in a real-world scenario. So grab a cup of coffee and let's get started. This is a recap of the function block that we reviewed in part 1 of this tutorial. As discussed in that tutorial, the function blocks has several types of outputs that can be used depending on the application. For this exercise, we will be using the PWM outputs. Since we will only be doing heating control in this tutorial, we are going to ignore the PWM negative output, which is for cooling purposes only. The PWM positive output is the pulse width modulated output for heater control. To understand how PWM is used in heating control, let's look at the electrical circuit first. This is a typical power circuit for a single phase heater. This is the first element in the circuit. A circuit breaker is an overcurrent protection device which opens during an overcurrent or short circuit condition, thereby cutting power to the heater. The relay allows precise control of power to the heater by controlling the on and off switching time of the relay. For PWM control, we need to be able to switch the relay on and off at high frequencies, typically in kilohertz range. A mechanical electromagnetic relay will not be suitable. For PWM switching, special relays called solid-state relays, or SSR for short, are used. SSRs play a crucial role in implementing PWM for heaters. Unlike mechanical relays, solid-state relays are electronic switching devices that have no moving parts. This makes them faster, more durable, and silent, perfect for rapid on-off switching required in PWM control. They can handle high switching cycles without wear and tear, ensuring long-term reliability. Solid-state relays are fast and precise. They can switch on and off at high frequencies, which is crucial for effective PWM and maintaining accurate temperature control. They have long life, since there are no moving parts and SSRs experience no degradation from mechanical wear, making them ideal for demanding industrial applications. And finally, SSRs generate less noise and electromagnetic interference compared with mechanical relays, thereby offering cleaner and highly efficient operation. So how does PWM apply to heaters in industrial temperature control systems? For heaters, precise control of energy is essential to maintain the desired temperature. PWM offers this control by adjusting the duty cycle, which is a ratio of on time to off time during a cycle. If we need more heat, we increase the on time, and if less heat is needed, we decrease it. This ensures the temperature stays consistent, even in systems with fluctuating demands. For example, this is the 25% duty cycle PWM signal. During every cycle, it is on for 25% of the time and off for the remaining time. For comparison, here are PWM signals with 50 and 75% duty cycles. By constantly adjusting the duty cycle, the controller is able to control the power delivered to the heater. For the SSR control, we will use Beckhoff's EL2809 digital output terminal. It has 16 channels and uses 24-volt logic level, which is suitable for my chosen SSR. A single terminal can control up to 16 heaters independently. With typical switching times in the range of microseconds, it is fast and suitable for PWM control. Now that we have covered the hardware side of things, let's hand over to Andrew, who will go over TwinCAT coding side of things.
Hello everyone, this is Andrew, and today I'll be walking you through the implementation of TwinCAT's temperature controller function. Let's begin. Start by creating a new TwinCAT project. From the dialog box, select TwinCAT project type and give a project a name. I'll go ahead and add a new PLC project. Our new PLC project has been created. I'll start by adding the required libraries to the references. The temperature control functions are available under the controller category. We need to add both these libraries. It can only be done one at a time. Next, I will create a folder for the function blocks and subprograms. Then I'll create our function block there. Now we can right-click on the folder and add a new POU. I'll select the POU type as function block and use structured text as the implementation language to write our code. I'll call our function block FB_temperature controller. First, let's declare all the required variables. Our function block will require some outputs, so I will declare those under var outputs. Next, I'll declare persistent variables to hold the controller PID tuning coefficients and other parameters. Finally, I will declare some variables for local use within this POU. Now for the fun part. Let's begin programming our function block. I'll collapse the declaration section to make more room for the coding area. I can use TwinCAT's Input Assistant to use my function block. In the Input Assistant dialog box, we can select instance calls to filter down to function blocks. Here, we can see my function block. I will select that and press OK. The Input Assistant populates the function block and exposes all its inputs and outputs. I will re-optimize the layout by removing the ones we don't need for this tutorial and only leaving the few important ones. Next, I am adding code to turn on a bit that indicates if the actual temperature has stabilized to our target set point for a specified period of time. Next, I will add code to switch the controller mode to active after tuning has completed. The function block has an enable input. If this input is false, then the controller should switch to idle mode. Next, we need a way to load the default parameter settings into the controller. I will add an action to this POU to handle that logic. With the magic of copy-paste, these are all the parameter settings with some default values. This includes the power controller settings like external tuning parameters, general parameters, setpoint parameters, and many more. Akio covered all these settings in detail in part 1 of this tutorial. Be sure to check that out to understand all these settings and their purpose. We can save and close. I will use this bit that we declared earlier to call this action program to load the default settings when we want to from the HMI. This line of code sets a bit to true when the controller is in active mode and has no errors. With our function block completed, we can now add code to instantiate this function block for use in our application. I will go ahead and add another POU of type program, which we can call from main. So in this program, I will loop through all the instances of the controller and pass in the set points and settings to each instance. All the user interaction will take place from the HMI, which we will review next. Okay, all the coding has been implemented. Next, let's take a look at the HMI visualization that I've already created for this tutorial. I will not be showing how the HMI was created, as that is outside the scope of this tutorial. We will focus on the application only. Let's put the HMI and code side by side. I will activate our solution and get the PLC running. Okay, PLC is in run mode now. Let's log in. Here, at the top, we have the status of the controller instances. We have parameters like requested state, actual controller state, fault status, etc. Currently, the controller is showing an active error about invalid cycle time. This is because we have not loaded the settings to the controllers yet. One of the settings is the cycle time information. I will go ahead and load the default settings. Now, I can run the controller by turning on the enable bit, which should clear the error. The error is now cleared, and our controller instance is in idle mode. For this tutorial, I have set up only 3 instances and named them Zone 0 to Zone 2. Here, you can see the other instances when I select different zones. They are also faulted for the same reason, so we will have to load default settings to all of them to clear their faults. I will select the zones and load the default settings for zones 1 and 2. And since the global start bit is turned on, all controllers are in run mode and should have their faults cleared immediately as I apply the settings. Now that the 3 instances are looking good, we can go ahead and test them. They're all in idle mode currently. Let's try the manual mode first for Zone 0. The manual mode allows us to set the controller output directly. Let's try setting it to 12%. We can see the output jumps from 0 to 12% immediately, and the heating indicator has turned on, as well as the PWM output indicator. Let's see what happens if we turn off the enable input of the controller. This disables it completely, and the output drops to 0, and the PWM output also stops. I will set up a scope to visually see how the PWM output and temperatures vary as we change the modes and set points. Okay, the scope is ready. Let's fire up the controller again. Let's try Zone 0 again in manual mode and see what the PWM output looks like at 12%. Now, we can clearly see the PWM output with a duty cycle of 12%. The process temperature shown here in blue rises in response to the heater activation. The process temperature has almost stabilized in response to the controller output. Let's try increasing the manual set point and see what happens to the controller output. The controller immediately increases the PWM duty cycle to the manual set point. You can see how the duty cycle is changing as I'm increasing the set point. At 100%, the PWM output becomes fully on and the heater will stay on. Alright, we had enough fun with manual mode. Let's switch it back to idle mode while I set a target temperature set point for some closed loop operation. Let's try a set point of 30 degrees Celsius and switch the controller to active mode this time. We can see several status indicators turning on. The controller PWM output is automatically adjusting in real time to control the process temperature based on actual process temperature, which we get from thermocouples fed back into the PLC. Notice how the at target indicator turns on as the process temperature stabilizes to 30 degrees. Let's try bumping up the target set point to 45 degrees now. The output reacts in response, and the process temperature can be seen rising steadily. Let's try one final set point. Next, I wanted to show the built-in self-tuning feature of the controller. For the self-tuning, make sure that the controller is enabled and have a target set point ready. I have set it to 10 degrees, and now set the E-control mode to tune. If you recall from part 1 of this tutorial, There is a tuning parameter, which is the wait time before performing the actual tuning. I have mine set to 20 seconds, so the actual tuning will begin after this period. After the tuning has completed, we should see the tuning PID parameter fields populated with the calculated values. We can either instruct the controller to use these internally calculated PID values or use externally supplied PID values. In my case, I am using external parameters. We can record these tune values and set these in the external parameter set. What about the other zones, you may ask? Well, so far we've only been playing with the first zone. The other zones are completely different instances of the controller and can be used to control different heating zone controlled by a separate heater and solid-state relay. Let's test it out. I will now switch to zone 1 and enter a different set point for this zone. Similarly, I will enter a different set point for the last zone and have all three zones working completely independent of each other. Now we can see all three zones are showing as active and have different set points and are modulating their outputs independent from each other. On the HMI, I can switch between the different instances and see how each instance is behaving. Here, I have switched zone 1 to manual mode, and it is now working in a different mode from the other controller instances. Zone 0 is still in active mode, and its output has long stabilized to the target set point. Meanwhile, Zone 1 was switched to manual mode, and its output is holding at 15% output duty cycle regardless of the target set point. Zone 3 was left at 50 degrees, and its process temperature has also stabilized to 50 degrees. I think we have covered mostly everything I wanted to show you today regarding TwinCAT's TF4110 controller. We covered the implementation and programming, as well as how to instantiate multiple controllers from one implementation using function blocks. Hope you enjoyed this tutorial.
That's all for today's video. If you have any questions or suggestions about today's video, please leave them in the comments below. If you found this video helpful, then please consider subscribing so you don't miss out on future tutorials. As always, thank you for watching and keep innovating.